Hello and welcome to part 4, the final part of the fluid flow and heat transfer in a mixing elbow tutorial series. In this video, we will explore the simulation results in ANSYS Fluent. We will visualize velocity and temperature contours, create vector plots, and examine profiles along key section of the elbow. This will help us better understand how the two streams mix and how heat is transferred in the junctions. Okay, so first of all, we'll start with display field contours of velocity magnitude on the symmetry plane. Okay, so for this post-processing, we are mostly use this results tab here. So first of all, for the velocity contour, we will go through the graphics, and under this contours, I will select a new contour. Then for the contour name, I will call it as contour velocity. Just ensure that field is enabled in the option group box here. Also, this node values and boundary values needs to be enabled in this options group box. And in this coloring, I will select the banded for this coloring part. And then under the contour of, I will select the velocity and velocity magnitude. And as I said, it's a velocity contour for the symmetry XY plane. So under the surfaces, I will select the symmetry XY plane. So now I can press on the save and display, but before that I will extend this part. You will see there's no contours here, but after clicking on the save and display, you will see one velocity contour has been added here, which is this one. So this is the contour we have here. So I will go to the XY plane by clicking here on this the blue Z-axis arrow here in this axis trait. So you are now in the XY plane. You can also use this toolbar here, for example, from the Z direction, which is this one. And then this fit to window, I can press on this one to have a view on the center of this graphic window. So you will see this is the banded value as we select here. If I select a smooth, you can see this is a smooth contour, but I'm going to show in a banded. So you will see if I zoom a little bit here and display, you will see there is some lines in this contour, which is a banded coloring type. So again, I will go to use the fit to window, and now I can close. And when you see, when you prop a point in the display domain with the right mouse button or the prop tool, the level of the corresponding contour is highlighted in the color map here. And also it is reported in the console. So for this point, the velocity magnitude is between 0.35 and 0.36 approximately. So you can just use right click on each point of this contour, and then you can see the velocity magnitude of the contour both in the console and also in the color map in the graphic window. Again, I'm going to create and display a definition, but this time for temperature contour in the symmetry plane. So again, in the results, graphics, and the contour, I will select a new contour here. For the name, I will call it as the contour temperature. And then here this field node value and boundary values will be selected. I will keep this smooth as the coloring, and then under this contour of I will select the temperature and static temperature. Again, select the surface symmetry XY plane here, and again save and display. You will see now we have two contour, temperature and velocity. Here this time I selected the smooth, so this is a smooth contour. So this temperature is in Kelvin unit, and it's a scientific format for the value. You can change this format in the color map, for example, here by selecting here, and uh, it's in the exponential type, so you can change to float with the number of precision 2, for example. Apply, and you will see it will be changed to another format. But I will keep as exponential for now and close this window, and again this one. This time I'm going to display velocity vector on the symmetry plane. So I will go again to results under the graphic, and then vectors. I will select a new vector here. Okay, for the name I will call it as velocity vector, vector velocity. Keep these items here, all the default. And the color by I will select the velocity and velocity magnitude, and under surface again symmetry XY plane, and I will press on the save and display here. And if I extend this part, you will see this velocity vector definition appears under the results graphics and contour tree branch here, under this tree branch here. So you can see all the newly created contours, vectors, and everything here. So you can see this auto scale option is enabled by default in this options group box. This scaling sometimes create vectors that are too small or too large in the majority of all the domain. You can improve the clarity, but by adjusting the scale and also the skip setting, thereby changing the size and number of vectors when they are displayed. So for now, I'm going to uh, increase this scale from 1 to 4. You can see it is like this, and then I will skip 2, save and display. So you will see the velocity vector here. Now I can press save and display, and then close this vector window. So now I can zoom in the display to see this velocity vector. So you can see in a closer view here. Again, I will use the fit to window, and now this velocity went to the whole domain. Okay, now I'm going to create a line at the center line of the outlet. So for this task, you can use the surface group box of the result tab. So here under the results and under the surface, I will go to the create and then use the ISO surface. You can find this ISO surface here. So I will click on the ISO surface. Okay, so to create the ISO surface, I will write a new name, for example, z equals 0 for the outlet. And then under the surface, I'm going to create this ISO surface based on the mesh that I have. So I will select the mesh, and then in the Z coordinate. So I will press on the compute here to obtain the extent of the mesh in the Z direction. The range of values in the Z direction is displayed in the minimum maximum box here. So I will retain the default value of 0 inches here for the ISO values, and then I will select the outlet, which is here, and then I can create the ISO surface. So I will press on the create. So if I go to this surface, I have this ISO surface. I can simply display here. So you will see I have this line. So to see exactly what is this line is, so I can go to the mesh. I will first display all these surfaces here, and in the outlet, if I select this newly added or created surface, Z equals 0 outlet, and display, you will see this line has been created here. It means that this actually line in the Z equals 0 with conjunction with the intersection with this outlet surfaces. So now we create this line here. So I can close these two windows. And now I'm going to display and save an XY plot of the temperature profile across the center line of the outlet for the initial solution. So I will go again to the results, plot and XY plot. I will select a new XY. So I will call this one as XY outlet temperature. I will keep this default setting, and the plot direction is in the X direction. It means that it is in this direction alongside this line. And then for the y-axis function, I will select the temperature, a static temperature, and under the surfaces, I will select this line, z equals 0 outlet, and then I will press on the save and plot. So you can also save the data of this plot in a text file. So you need to click on the right file. I will do it for now. So click here. So you will see when you click and check this option, write to file, this save and plot will change to the right. So if I click here, I can save this data to a file. I will call it outlet temperature 1 for XY plot, and then press OK. So this file will be changed. So I can close this solution XY plot for now. And under this plot, on XY plots, you will see now you have this XY plot. So now I'm going to define the dynamic head formula with a custom field function. This formula here in the ANSYS Fluent. So if I bring it down, I can use the user define and the field function for this formula. So I will go to the user define, and under the field function, I can use the custom field function. So this is the custom field function calculator, as you can see. So I'm going to select the density on this field function. So I will select the density here and then click on the select. So you will see you have the density here in this definition. Then I need to add the multiplication symbol to this definition field. So I will use here, just click here. So you will see you have it here on this definition. Next value is the velocity magnitude. So I can go again in the field function to find it. So I will select the velocity magnitude, and then press on the select here. So you will see the velocity magnitude also has been added here. Then here I will click on this button, to raise actually the last entry in the definition field to a power. So I will click here and then click on the 2 for the power. So now you will see this is density, velocity, magnitude, and this is power 2. And then I will select this button to add the division symbol and then click again on 2 here. So now I have this formula here. You will see density here, density, velocity, magnitude, power 2, and then uh, division symbol, and then again 2. Okay. And then for this new function name, I will call it as the dynamic head here. Okay, so now I can define this custom field function by clicking on the define, and then I can close here this window, and this dynamic head tree item will appear here under this parameters and customization, and then under this custom field function you will see the dynamic head here. So again, I will go to the results, and then under the graphic, under the contour, I will select a new contour for this dynamic head. So I will call this one as a contour dynamic head for the contour name. I will select the banded here for the coloring, and I will display these boundary values in this option field. And then for the contour of, I will select the custom field function, and I have this dynamic head here, so I will keep it as dynamic head here. And to show on the symmetry XY plane, I will select this surface as symmetry XY. Now I can press on the save and display, and again another contour for a dynamic head here. So you will see this dynamic head contour also. So now for this custom field function, I'm going to save the case and data file. I will press on file and write, and then case and data. I will call it as 3D elbow 1 here. But when you write the case and data file at the same time as I'm doing now, it doesn't matter whether you specify the file name with a, I mean here, case or that extension, as both will be saved here. So I just change it to elbow 1 and then press on OK. So let me close this window. For the first run of this elbow tutorial, we have solved the elbow problem using a fairly coarse mesh. The elbow solution can be improved further by refining the mesh to better resolve the flow details. ANSYS Fluent provides a building capability to easily adapt and locally refine the mesh according to the solution gradients, which call it as the adapt mesh. So in the following steps, you will adapt the mesh based on the temperature gradient in the current solution and compare the results with the previous results. Okay, so to do so, we need to define cell register to adapt the mesh in the regions of high temperature gradient. So what we should do, we go to the solution here in this tree, and under this solution, you can select the cell register, right click on it, new, and then you select the field variable, as we are adopting the mesh based on the high temperature, and this variable will be temperature gradient. So I will select this field variable register window. Okay, so for the type here, I will select one option called as cell more than. So the cells are the value of more than something. So I will select this option. Then I will, under this part, I will select the curvature. So I will select the curvature, and under the curvature of, I will select the temperature and the static temperature. So after that, I will click on the compute. So you have the minimum and maximum value. So Fluent will update the minimum and maximum values to show the minimum and maximum temperature gradient. The average temperature gradient and the standard deviation will also be displayed. So I will enter a value of 0.0015 for the cell having a value more than. So this is 0.0015. So now I can press on save, and even save and display also here. You will see this parts will be selected later with this. These are the cells that have value more than this value 0.0015, which has been selected here. So I will save and then close this window. And as you can see, we have this field here. So now we're going to set up mesh adoption using the cell register that we have created now. So for this task, you will use the adopt group box in the domain here. And under this domain, you can go to the adopt and use this manual. So this manual mesh adoption will be open. So here you can select the previously define curvature 0 here, cell register here for this refinement criterion. So ANSYS Fluent will not coarsen beyond the original mesh for a 3D mesh, hence it is not necessary to select the coarsening criterion in this instance here. So I can just click on adopt. It will take a little bit time, and you have some information here, and then you can display. So you will see those part of meshes that we have selected in the cell register with the name of curvature 0 actually will be selected here, and the mesh will be refined here. So you'll see this ANSYS Fluent is displaying these cell marks for adoption in this graphic window here. And you can also change the way the Fluent displays a cell mark for adoption by performing some steps. I can show you if you click on the display option here. So you have this window. First, I will select this option, draw mesh here, and just be sure that only the edges will be selected here. So I will disable the faces here, and I will remove this Z equal outlet also. All the surfaces except this Z equals 0 has been selected, and in the edge type I will select all, and then I can display and close the mesh display. So you will see here. So I can close this window now here, and then I can select OK in this, and again display. So you will see all this adoption part beside the meshes that you have. And I will go here and then select this that direction and fit to window again. And now I can close this window now. So let's go to display this adoption mesh. So I will go to the mesh display here. So just make sure that this edges, only this edges has been selected here, and in this part edge type I will select all, and then I will first deselect all the surfaces here, and just select this symmetry XY plane. And then after that, I can click on the display and close this mesh display. So if I zoom in a little bit here, you will see uh, before this mesh refinement, the meshes was like this polyhex core type mesh, but now most of these meshes here in this region with the high temperature gradient actually adapted and divided into some smaller mesh. So you will see, for example, one mesh changed to 6 meshes like this, and so we have better and finer mesh here in this part in this parts to see the uh, results in this new meshes actually. So again, we need to run the calculation. So I will just select this fit to window. So again, I will go to the solution and keep this 150 and start the uh, calculation by pressing on the calculate button. So this is again, we can check this residual. I will use the sub window view to see all beside each other. And the solution will converge as you can see here. So you will see all the equations are going to reach the convergence, this one, and also this outlet temperature. So we will wait for a few seconds to reach to the convergence, and then we will save the case and data file for this solution with the adapted mesh. So I will press on OK, and then I will go to the file and then write both case and data file. I just only change this one to elbow 2 and then press OK to save the new data. Okay, now I'm going to display the temperature distribution using node values on the revised mesh using the temperature contour definition that I created earlier. So I can go here under these contours for the temperature. So I can just simply here right click and then display the contour. So this is a new contour temperature that we work on the refining the mesh in this area. Actually, now I can display the XY plot for the outlet here. So I will click here, edit, and then save to display. Okay, so like the previous XY plot, I will use this option, write to file, to save this the data of this plot here. So first of all, I will just again save and display, and then click on the write to file, press on the right here, and then I will change this one to 2xy, press OK, save again, and then close this window actually here. So now I'm going to display the outlet temperature profiles for both solutions on a single plot. So to do so, I will go to the results, and under this plot, I will select the data sources here. So I will select this data source here. So now I will use the previously saved file. I will use the load file to load those two files, outlet temperature 1 and the outlet temperature 2, both XY plot files. So I will press on OK here. So in the data source name, I have these two XY plot data. Okay, now I'm going to change this legend name for these two XY plots. So I will select here this one. So as this data is for before adoption, so I can change this legend here. Instead of this one, I will change it to before adoption, and then here I can click on the change legend entry. So you see it will be changed to this one. So in a similar way, I will change the legend entry for the second plot after adoption. So I will deselect this one and select the second plot and change to adopted mesh, and then click on the change legend entry here. So now if I just click on the plot, you will see both static temperature of XY plot in that surface, but before and after adoption. So you will see the data after adoption has been increased a little bit. So you can perfectly compare these two plots together. So it's a very useful window in the tools that you can use to display your XY plot, for example, here. So now I can close this. Okay, that concludes our fluid flow and heat transfer in a mixing elbow tutorial series. We've gone from creating the geometry in a SpaceClaim to meshing in Fluent Meshing, running the simulation, and finally analyzing the results. I hope this series helps you in your own ANSYS Fluent project. Thanks for watching and see you in the future tutorials.